Hello everyone. We continue with 5.3 optimization problems involving exponential functions. I'm going to go through two examples with you. Let's look at the first example. The concentration C in milligrams per liter of a tracer chemical in the bloodstream T hours after its injection is given by the formula C of T equals e to the power of negative T minus e to the power of negative 3T. Part A. Determine the maximum concentration of the chemical. When does this occur? So this is like any other optimization problem. So we are going to use the same method when solving. We are going to take the first derivative and find the zeros of the first derivative. Okay, so derivative of e to the power of negative t. So e to the power of negative t times, we are going to multiply this by the derivative of the exponent. That gives us negative 1 minus derivative of e to the power of negative 3t gives us e to the power of negative 3t times derivative of the exponent negative 3. So let's simplify this a bit. So negative e to the power of negative t plus 3 e to the power of negative 3t. So since we're going to make this equal to 0 and solve for t, we need to factor. So we see that e to the power of negative 3t is the common factor. So that gives us negative e to the power of, subtract the powers, negative t minus negative 3t gives us 2t plus 3. Okay, so I would like to also factor this negative sign out. Negative e to the power of negative 3t e to the power of 2t minus 3. Now I'm going to make the first derivative equal to 0 and solve for t. So as you see, we have two factors here, factor 1 and factor 2. So if I take the first factor and try to make it equal to 0, okay, so we will get no solution because this will never be 0. So think it this way, substitute any value for t. It can be a positive number or a negative number. So you will never get 0 here. Okay, so we can't make it equal to 0. So this will not work. Then we are going to get our 0 from the second factor. E to the power of 2t minus 3 equals 0. E to the power of 2t equals 3. Now we can take the ln of both sides to solve for t. Ln e to the power of 2t equals ln 3. Now let's use the power rule for logarithms. So we get 2t times ln e equals ln 3. And previously we learned that ln e is same as log base e of e, and that is equal to 1. So basically we get 2t equals ln 3. So now we can divide both sides by 2 and we get ln 3 over 2. Now we can use our calculator to calculate the decimal value for this. Ln 3 divided by 2. So 0.55. So approximately this is 0.55 hours. Okay. So we can also make a first derivative table to see this is really giving us the maximum. 0.55. So since this is a word problem and time cannot be negative, so we're going to start our table from 0 and the other end is just infinity. Okay, so we're going to check the sign of the first derivative and we are going to see where the original function is increasing or decreasing. So let's pick a value in the first interval from 0 to 0.55. So let's pick 0.5 and then sub in the first derivative to see if it is giving us a positive or negative value. So our first derivative is negative e to the power of negative 3t e to the power of 2t minus 3. So I'm going to sub 0.5 here, e to the power of negative 1.5, e to the power of 1 minus 3 to see if it is giving us positive or negative value. So if this negative sign is here, e to the power of negative 1.5 is same as 1 over e to the power of 1.5. So this is a positive value. Again, I don't need to calculate this using a calculator. I just need the sign of it. That is the reason I can just analyze it this way. And this one, E is 2.72 approximately. So 2.72 minus 3 is going to give you a negative value. So basically, we get negative times negative, which is a positive value. So for the first interval, we get that first derivative is positive. So let's check the second interval. So we need to pick a value that is greater than 0.55. How about if we pick 1? So let me sub 1 in the first derivative. So negative e to the power of negative 3, e to the power of 2 minus 3. So this is negative. So we sub 1 here. So again, this gives you 1 over e cubed. So that is a positive value. And this one, 2.72 square minus 3. So that is obviously greater than 3. So that gives us positive. So negative times positive gives you a negative value. So now we know that first derivative is negative in this interval. Okay. So based on that, we can say that C of t is increasing in the first interval and decreasing in the second. So then we can see that we have a local maximum at 0.55. Okay. So the x-coordinate of it is 0.55. Now we need to calculate the y-coordinate of it because the question is asking you what is the maximum concentration and when does this occur. We know that it occurs when t equals 0.55 hours, but what is the maximum concentration? So we can just sub this 0.55 in the original function to get the concentration level. So that is e to the power of negative t, e to the power of negative 0.55 minus e to the power of negative 3 times 0.55. So we have e to the power of negative 0.55 minus e to the power of negative 1.65. Okay, so now we can use our calculator to calculate this value. So e to the power of negative 0.55 minus e to the power of negative 1.65. So this gives us 0.38. 0.38 then is the maximum concentration. So we can say that maximum concentration is 0.38 milligram per liter, and it occurs at t equals 0.55 hours. So let's look at part B. Determine the coordinates of any points of inflection for C of t. So to get the points of inflection, we need to take the second derivative. So we know that first derivative is, actually I'm going to use not factored form here. So negative e to the power of negative t plus 3 e to the power of negative 3t. So it is easier to take the second derivative from here so that we don't have to deal with the product rule. Okay, so negative derivative of e to the power of negative t, e to the power of negative t times derivative of the exponent, negative 1, plus 3 derivative of e to the power of negative 3t, e to the power of negative 3t times derivative of the exponent, negative 3. So this gives us e to the power of negative t minus 9 e to the power of negative 3t. Again, to find the points of inflection, we need to find the zeros of the second derivative. So we are going to factor this. E to the power of negative 3t is a common factor, and we get e to the power of 2t. Again, so you are dividing e to the power of negative t by e to the power of negative 3t, therefore you are subtracting the exponents. So minus 9 we get. Okay, so then we have two factors here. First factor, e to the power of negative 3t. second factor, e to the power of 2t minus 9. Again, if we try to make this equal to 0, it's not going to work. So this factor will never be 0. Then we can get the 0 from the second factor. So e to the power of 2t minus 9 equals 0. E to the power of 2t equals 9. So like part A, to be able to solve this, we are going to take the ln of both sides. So ln e to the power of 2t equals ln 9. Use the power rule of log. So you get 2t times ln e to the power of e equals ln 9. Again, ln e is equal to 1. So we get 2t equals ln 9. T equals ln 9 over 2. So let's calculate the decimal value for it. Ln 9 over 2 gives us approximately 1.1. So t equals 1.1 hours. So let's do the second derivative table if it really gives us the inflection point, because we know that we have an inflection point if concavity changes. So let's check the sign of the second derivative. Again, I will start the time from 0 and the other end is infinity. Okay, so let's pick a value between 0 and 1.1. Let's pick 1. So I'm going to do the work on a separate paper. So again, I'm checking the sign of the second derivative here. So e to the power of negative 3t, e to the power of 2t minus 9 is the second derivative. And I'm going to sub 1 here. So e to the power of negative 3, e to the power of 2 minus 9. So e to the power of negative 3, again, so if you write it with a positive exponent, it gives you 1 over e cubed. That's a positive value. E square, so you're looking at 2.72 square approximately, and that's going to be less than 9. So then we get negative here. Okay, so positive times negative gives you a negative value. So we got negative for the first interval. Now we're going to check the second interval here. So we need to pick a value that is greater than 1.1. Let's pick 2 and sub in the second derivative function. Okay, so e to the power of negative 6, we are subbing 2, e to the power of 4 minus 9. Okay, so this gives you 1 over e to the power of 6. So that is a positive value. So this is 2.72 to the power of 4 minus 6. Even if it was 2 to the power of 4 would be 16. So looks like 16 minus 9 obviously is positive. So this will give you positive. If you are not sure, of course, you are welcome to use your calculator. So positive times positive gives you a positive value. So we got that second derivative is positive in the second interval. So based on that, we can check the concavity of the original function. So second derivative is negative, function is concave down. Here, second derivative is positive, function is concave up. So concavity is changing at 1.1. So therefore, we have a point of inflection at 1.1. Okay, so let's find the y-coordinate of the point of inflection. So we need to substitute 1.1 in the original equation. So original equation is c of t equals e to the power of negative t minus e to the power of negative 3t. So we are going to sub 1.1 here. We get e to the power of negative 1.1 minus e to the power of negative 3.3. E to the power of negative 1.1 minus e to the power of negative 3.3. So that gives us 0.29. It's almost 0.3. Okay, so this is 0.3. So the y-coordinate of point of inflection is 0.3. So that is the part B. Let's look at part C. It says Determine the limit of c of t as t approaches infinity. So I'll just do it this here. I don't have enough space. So c, limit of c of t, so limit of e to the power of negative t minus e to the power of negative 3t as t approaches positive infinity. Okay, so basically you can substitute kind of a very big positive value for t to check the limit. Okay, so how about if we substitute, let's say 100, so e to the power of negative 100 minus e to the power of negative 300, so this gives you 1 over e to the power of positive 100, and this gives you 1 over e to the power of positive 300. As you see, you are dividing 1 by a very big number, so this is the limit of it is almost 0, so it is 0. And then second part, same thing, you are dividing 1 by a very big positive number, so that is a very, very small positive number. It is almost 0. So limit of this is 0. 0 minus 0 gives you 0. So this limit is 0. And again, from the first video, we learned that so limit of the function as t approaches or x approaches infinity is giving you the equation of the asymptote. So basically, this is also our asymptote, horizontal asymptote, that is y equals 0. Next part is say sketch a graph of c of t, and that's what we will do. So let's put our local max. So we have 0.55, 0.38, 0.55, and 0.38 somewhere here. Okay, so that is 0.55, 0.38. And let's put also our point of inflection. We have 1.1 and 0.3, 1.1 and 0.3. Okay, so let's also check the start point. All right, so when t is 0, if we sub 0 here, we get e to the power of 0 minus e to the power of 0. So 1 minus 1 gives you 0. So start point is 0, and it should make sense when time is equal to 0. So medication is not taken, or the chemical is not taken. Therefore, the concentration is 0 when time is equal to 0. Okay, and we also have this horizontal asymptote at y equals 0. Actually, in this case, it is c equals 0. Okay. All right. Now, actually, because it is a very simple graph, I will not join these two graphs, but I can just follow the concavity to sketch my graph. So the original function is concave down when t is between 0 and 1.1. So it is going to be concave down, and I have to pass through those points up to 1.1. And then after that, the function is concave up. So I'm going to draw something concave up here, and then there's an asymptote. So I need to approach to that asymptote. And this would be the sketch of this function. So I'm going to do another video for the second example.